do a record to the cloud? Last time I think I did it on my computer and I can't find it.
That works now. I have the recording thing button.
Oh, okay. Okay, just give it one more minute, I guess. Okay, Antoine, I think you can go ahead and get started with the introduction.
Yeah, sure. So hello everyone. Thanks for joining us today in the CNET seminar session. So today we're welcoming Alejandro Flores as a guest speaker. So Alejandro received a PhD degree in hydrology from the MIT, Massachusetts in 2009, and he is right now an associate professor with the Department of Geosciences in the Boise State University. And his research interests include terrestrial system modeling, remote sensing, data assimilation, and integrated human hydrologic system modeling. And today he's going to talk to us about rain or snow. What does cloud microphysics have to do with controlling water delivery to the critical zone? So thank you, Alejandro, for doing this, and this is your time to speak now.
All right. Thank you, Antoine. Thank you, Armide, for the opportunity to chat with you all. I'm assuming that you all can see the slides here and everything.
Yes.
Great. All right. So first off, what I want to do is, even though I'm, presenting today, like most science and research these days, what I'm going to present to you today is the result of a large team effort. My role in it was sort of securing the funding and sort of orchestrating some interactions and doing some advising. This is largely the work of my former PhD student, William Rudisil. Will is now a postdoc at Lawrence Berkeley National Lab. And this is sort of two publications, one that's in press and one that is still in review, but should be sort of coming out in maybe the next 6 months or so. And just by way of background, I'm a hydrologist by training, but have sort of navigated into this sort of space that's right at the land-atmosphere interface in trying to sort of communicate to some of the atmospheric scientists sort of the ramifications of some of the ways that atmospheric processes are treated in coupled land-atmosphere models for land surface hydrology and ultimately for sort of critical zone hydrology and hydrologic science more broadly, but also trying to communicate to hydrologists the fact that they should press on the atmospheric scientists to sort of better communicate what's going on in the atmospheric models, so that they have a better understanding of how the models that atmospheric scientists develop sort of impact the hydrologic states and fluxes that we all as sort of critical zone scientists are sort of concerned about. So as I get started today, what I want to do is really kind of motivate this by a picture, right? And a landscape that the landscapes that I work in and I'm particularly interested in. I literally took this picture last week. This was sort of at a small conference that one of my colleagues organized in a place called Stanley, Idaho. It's in the Sawtooth Mountains or near the Sawtooth Mountains, which you're seeing here, right? And this is sort of the first significant dusting of snow that the Sawtooths have received this season. And at the foreground, you can also sort of tell that down actually in the town of Stanley, which is a tiny town, but a beautiful place, what you can sort of see is that, there's rain falling in the morning, right? So the higher elevations got snow, the lower elevations here got rain. That's going to shift as we move into the winter. This whole area will be snow covered, but we're really interested in sort of this rain snow transition zone. And a lot of you that have maybe don't necessarily have the experience with it, or have maybe just seen the rain snow transition in pictures in places like Colorado or California, may be accustomed to think about it as sort of a single elevation at which, precipitation sort of is rain liquid form below and frozen and snow above. But if you take a broader look, stepping out at the entire, Western United States, this is work by Zion Kloss in 2014, a really nice kind of mapping of what the sort of proportion of precipitation in an average year sort of falls as rain or as snow. And what you see is that there's a huge gradient of landscapes all throughout the Western United States that sort of have this mix of rain and snow. And so the rain snow transition isn't necessarily just sort of one elevation at which the precipitation transitions from rain to snow, but rather it's a large region over which there's a mix of precipitation that over the course of the year that falls as rain or as snow. Now, this has really profound implications for sort of the downstream hydrologic response, right? So the phase of precipitation as it falls makes a really big difference in terms of the hydrologic response. And so on the right here is a conceptual diagram from a really nice review paper that Adrian Harpold led in 2017 that sort of is actually also titled Rain or Snow, right? But is talking about how well we're actually observing or modeling this rain-snow transition and its implications for downstream hydrologic response. And in the cold season, right, if you get your precipitation or how you partition that precipitation as either rain or snow, right, and they go through a whole bunch of different sort of index-based approaches based on primarily temperature and humidity for how you decide if precipitation is occurring as rain or snow. But depending on whether or not you overpredict the proportion that's falling as rain or the proportion that's falling as snow, you produce some very profoundly different sort of hydrologic responses, right? Either you're over assigning precipitation to different sort of buckets in the land surface hydrology response, right? If you're over predicting rain, you might get sort of too much infiltration, which will lead to an earlier release of water to vegetation and to sort of the downstream hydrologic response. If you assign too much to snow, you can then sort of delay that sort of that timing and magnitude of hydrologic response. And it also has really profound implications for base flow, right? And we think of this not as just a prediction issue, but also in the context of climate change, right? As you imagine, right, this landscape that's warming pretty dramatically, we expect the zone of this rain snow transition to sort of expand through time, and the rate at which it expands and the landscapes into which this rain snow transition expands has a really profound impact on these sort of hydrologic responses, on the ecosystems that depend on the water that comes as either rain or snow. The critical zone itself, right? The biogeochemical reactor that's processing nutrients and metals, the potential shift from more snow-dominated to more rain-dominated systems has really profound implications for that sort of subsurface biogeochemical reactor as well. So just kind of motivating, the narrow slice of work that I'm going to talk about today in this sort of broader landscape issue, this broader issue of sort of rain-snow transition. Here's some sort of motivating issues and questions that sort of drive this research, right? So as I mentioned before, and as Antoine introduced me, right, I'm trained as a hydrologic modeler. And one of the first things I did when I got to Boise State was that was interested in applying some of these hydrologic models in these sort of beautiful mountain landscapes. And the thing that you very quickly find is that the lack of meteorological forcing, so the precipitation, the temperature, the humidity, the wind speed, the solar radiation forcings, the coverage of those meteorological forcings in adequate spatiotemporal detail to resolve some of these high resolution hydrologic state variability is really limiting, right? So you find a lot of products out there that are very frequently too coarse in either spatial or temporal resolution to be able to sort of resolve some of the scales of variability that we as hydrologic scientists care about. In the past sort of maybe decade or so, there's been a lot of work in sort of the regional climate modeling space that's pushed the resolution of these regional coupled land atmosphere models, these regional climate models, down to spatial scales at which we can start resolving or permitting at least some of the convective movements that are associated with sort of forced convection or interactions between the atmosphere and topographic features, at least at sort of the spatial scale of mountain ranges, right? Not necessarily sort of hill slope scales, but the scale of those mountains that I showed you in that picture, right? So those mountains can be resolved in those models, at least to some extent. They can result in forced convective motions that can create the rates of precipitation that are broadly observed in observations, but we have to move down to sort of order kilometer scales, right? So scales that are beneath about 4 kilometers at the very coarsest. But right, as I moved into sort of starting to use some of these models to generate these forcings, some of the things we found is that commonly used models like the weather research and forecasting model, which I'm going to talk about extensively today, they're not so much models per se, as much as they are modeling frameworks that require a bunch of choices to configure them for the landscapes and the situations in which we're running them. And on top of that, those choices have really profound implications for the partitioning of rain and snow, the amount of precipitation that we get, and obviously sort of then the downstream hydrologic response. But evaluating these model outputs is challenging, right? So benchmark data sets, a variety of benchmark data sets exist to potentially help us identify the errors and biases in these data sets. But as we'll illustrate, they are often not entirely independent of one another. And so some of Will's work, what I'm going to get to sort of at the end of this talk, relates to how can we evaluate some of these precipitation data sets from these convection permitting climate models in a context that we as hydrologists care about, right? So what we're interested in is, did this precipitation data set produce the hydrologic response, or how likely is it that it could have produced the hydrologic response that we actually observed? So to motivate kind of the first part of this talk, I want to present to you what I broadly talking about is the modeler's dilemma, right? So as I mentioned, a lot of these complicated models that we have in sort of the regional climate modeling space and in the hydrologics, modeling space, as I mentioned, they're not necessarily sort of models per se, but they're often modeling frameworks, and they require us to make certain choices about how we represent certain physical processes. And in doing so, we have to ask ourselves, okay, so which of these options for a given process, which option that's available to me is the most physically realistic? At the same time, which option produces the best results in terms of representing or capturing the observed hydrologic variability or meteorologic variability that I care about? And unfortunately, the answer is often not the same, right? So some of the what we think of as more physically realistic options might sort of be associated with some biases or errors that are potentially problematic for the particular context that we're interested in, right? So this is one of the choices that we sort of face. And the particular sort of choice that I want to present to you today, the choice that we have to make is this, this idea of the choice of how we represent the microphysics in these coupled land atmosphere models. Now, what do the microphysics control? So this is a sort of beautiful conceptual diagram that Will put together. I think he did this as he was finishing his dissertation, was looking for some artwork to do, and when he wasn't sort of doing some, data analysis. But this is sort of a nice conceptual overview of really what the cloud microphysics are, sort of the processes that they're trying to represent, and the ultimately kind of the ramifications of how we think about and represent those processes numerically and mathematically, how they affect the sort of the hydrologic fluxes that we care about, in particular, the precipitation and that sort of fraction of precipitation that's occurring as rain or snow. So these microphysical processes, right, which their heritage is long in the atmospheric sciences, a big motivator for these processes is actually aviation safety, right? So, these processes control, how likely it is that you might get icing on your wing as a pilot, right, which is a big safety of flight issue. But they obviously sort of have very profound implications for things like cloud cover, and snowfall and precipitation intensity. So, we're talking about how do we represent sort of the nucleation or the evolution of cloud and ice water droplets. How do those grow, right? How do they interact with one another? How do they grow through rhyming? How do they grow through aggregation? And then ultimately, in which dimensions do they grow, right? What assumptions do we make about the shape of those hydrometeors? And how do what do those assumptions about the shapes of those hydrometeors, what ramifications do they have for the rate of growth? And ultimately, what do those assumptions about those processes, the shapes of the hydrometeors, the way that they grow, the way that they sort of aggregate, how do those ultimately control the terminal velocity of those particles, which is ultimately sort of, what controls how much water is going to sort of fall out of the atmosphere and in which phases. And so there are a variety of different sort of what we call as parameterizations. So you can think of these as sort of different ways of representing these microphysical processes that are available for us to choose. And they all sort of make different, very plausible assumptions about the way that these microphysical processes work. But as you might imagine, and what I'm going to show you is that they involve, they have ramifications in terms of the predicted precipitation that are potentially really important to us as hydrology, right? That will have profound influences on where precipitation occurs, the rate at which that precipitation occurs, and ultimately the timing and delivery of that precipitation to the critical zone. Before going further, I want to also sort of say that there is, I'm going to present to you the results of some numerical experiments that Will ran. I'm only going to talk about the microphysical processes, but as I alluded to, there's a whole broad range of microphysics or of other processes that are at play in these models. But we're going to focus here on the microphysics options. And so if there's anybody here that has familiarity with the weather research and forecasting model or models like it, other global climate models use some of these parameterizations as well. Will conducted a numerical experiment where he used 3 different microphysics schemes and kept all of these other sort of processes the same. So some details about those numerical schemes. I'm going to show you the domain in a second, but it involved, this is centered over the central Colorado Rockies. There was a 3-kilometer domain with a 1-kilometer domain within it. So these are nested grids. Will ran all of water year 2018, which is a very dry year, and all of water year 2019. He focused on October through May, right? So the cold season, the snow season in the Colorado Rockies. As a lateral boundary condition data set, he used the climate forecast system's second version, so the CFS v2 data. And he used sort of three different microphysics schemes. The Thomson scheme, which in WRF and on subsequent figures you'll see as MP08. The Morrison scheme as MP10. And then this newer scheme, which is often referred to as Ishmael, which is option 55 in the weather research and forecasting model. And I'm not going to get too much into sort of the ways in which the cloud microphysics treats these processes, but right, we these three sort of microphysics schemes, you can think of them as Thomson and Morrison, resolving sort of these the hydrometeors themselves slightly differently in terms of some details about the shapes of these microphysics schemes. And then the Jensen scheme is a much more complicated scheme. So we think of this as sort of perhaps even more physically realistic, right? It relaxes some of the assumptions that the Thomson and Morrison schemes makes. But as you might imagine, with that comes sort of added computational burden, right? So it takes a lot more, computational power and a lot more time to run simulations with this Jensen scheme than it does Thomson and Morrison. Will took the outputs of the weather research and forecasting model and did some offline runs with the NOAA MP land surface model. And he did that so that we could compare the outputs of the land surface model and the way that these different realizations or different scenarios of the forcings, right, the ramifications that those have for the development and the evolution of the associated snowpack, right? So we're simulating the spatial distribution of snow depth and snow water equivalent. And we have a pretty unique data set called the Airborne Snow Observatory, which is an aircraft-based LiDAR platform for observing the spatial distribution of primarily snow depth, but they also sort of produce a product that is the retrieval of snow water equivalent in that region. So here's the full WRF domain. These are the Colorado Rocky Mountains. So for those of you that are somewhat familiar, Denver is sort of right about here. Colorado Springs is sort of right about here. This is called the San Luis Valley. And we're focusing on a watershed here right in the middle of the domain called the East River watershed. This is a focus area for the Department of Energy's Office of Science, Environmental Systems Science program. It's a large sort of community critical zone observatory that is funded by the Department of Energy, but a lot of folks, including some folks there at University of Illinois. It's completely plausible some of you are doing field work in the East River. There's been a lot of focus on this, on watershed function processes in this watershed. So we're going to focus some results here on the East River. The purple triangles that you'll see here are the different SNOTEL sites. So these are stations at which we have observations of precipitation, snow water equivalent, snow depth in the broader region. So I'm going to start presenting some of the simulation results, but before we get into too much of the results and how these different microphysics schemes lead to different predictions of precipitation and subsequently snow depth and snow water equivalent, I do want to sort of caution that when we compare these different microphysics schemes or the results produced by these different microphysics schemes, I want to sort of couch that in the context that this is often a sort of different apples to oranges comparison. So like I said, these different microphysics schemes make different assumptions about how cloud microphysics are actually working. And the way that they do that is that they'll assign parts of the hydrometeor, they'll assign particles to buckets with different names, right? So, for those of you that are land surface hydrologists or hydrologists, in the near surface, you can think about this as the difference between, sort of having a 3-layer versus a 10-layer vertical soil moisture model, right? So the same kind of approximate thing is going on here in the cloud microphysics. So, some of these models, right, don't have a bucket that's actually called snow. Instead, the Ishmael model, for instance, the Jensen model has 3 different buckets of ice, right? Whereas Thompson and Morrison have an actual bucket called snow. So, when we plot all of these together, we can sort of start to see some analogs to one another, right? So if we take a look at this image, so this is height in the atmosphere above the land surface, and this is the mixing ratio in these different hydrometeor buckets. You can start to draw analogies kind of between these different schemes. So we can say, well, Thompson and Morrison explicitly have a snow bucket, but then when I look at this MP55 ice 1 bucket, it appears to be sort of doing what the snow bucket is. So maybe it's the best analogy for this snow bucket. So, all of that's to say, in the following results, right, there's a whole bunch of the microphysics that, I'm not going to present today, but suffice it to say that sort of comparing across these schemes gets complicated very quickly because just of the different ways that they're representing these hydrometeor sort of buckets. So here's some results from a transect through that East River watershed that I'm going to show. And what I'm going to do is on the top row here, as I kind of reveal these results, I'm going to show you this is going to be water year 2018 across the top. The accumulated precipitation for this water year associated with each of these different microphysics schemes is going to be presented in a different color. So this is water year or cold season precipitation along this transect, right? The precipitation values are right here. So this is for water year 2018 across the top. It'll be for water 2019 across the bottom. You'll see that the scales are very different. As I mentioned, 2018 was a much, much drier year. 2019 was a wetter than average year. What you're going to see here plotted in the shaded red and blue is the different season average wind speeds, vertical wind speeds associated with these simulations, and the mixing ratios for what we can think of as most closely that snow bucket, right, in these different schemes. And what I want you to pay attention to here is, right, the mixing ratios as we go through and step through these different schemes are going to change. But I want you in principle to kind of, I want you mostly to notice how it's affecting how we're predicting the location of the peak snow or the peak precipitation and the magnitude of the peak precipitation through this landscape. So here is for sort of the first scheme. If we add on the next scheme, right, so this is the comparison between Thompson and Morrison, we see broadly that in the dry year, they result in largely the same precipitation. Oh, the other thing that I should mention here is that the wind speed in these simulations is generally from left to right. So you can think of the winds as generally advecting moist air from the left side of this plot to the right side. And you see sort of the associated accumulation of precipitation associated with that, right? So the Morrison scheme here tends to result in a little bit more precipitation on the upslope side, but they're largely tracking similarly in the downslope side. That flips a little bit in the water year 2019, where the Morrison scheme is actually producing a little bit more precipitation at lower elevations than the associated Thompson scheme. But then when I add this Ishmael scheme, right, some more interesting sort of things start to pop out, right? So if we look along these transects, this Ishmael scheme, which again, I said we think of as being sort of the more sophisticated scheme, is producing more precipitation in the wetter year, in some places up to 2 times the precipitation that the Thompson scheme is predicting, further downstream of the topographic barrier here, right? So clearly, you know, the choice of these schemes is having a really big implication on sort of, in particular, the precipitation that's predicted at lower elevations downstream of our sort of largest topographic barrier that the winds are encountering as it sort of enters the landscape of our computational domain. So if I move forward, right, we would want to ask ourselves, well, you know, as hydrologists, okay, so which of these which of these are more correct, right? Which of these sort of are associated with precipitation patterns that are more realistic? And in these mountain landscapes and more broadly, right, it's a difficult question to answer because, you know, the spatial distribution of precipitation, particularly at high spatial resolutions, is pretty difficult to observe. But on the other hand, right, the one advantage we have in these snow-dominated landscapes is that precipitation is leaving a signature behind it that is persistent through time. And that is in the form of the snow that's actually on the ground. And actually, when you talk to a lot of snow scientists, sometimes they'll actually interchange, you know, changes in snow depth for precipitation, right? Which is an interesting thing to think about as sort of a hydrometeorologist, but right, there's a strong sort of tendency to think about the snowpack as leaving an imprint of the precipitation that we can then use to sort of evaluate, you know, which of these different microphysics schemes might be producing sort of more realistic results. So the Airborne Snow Observatory data, like I said, this is a LiDAR-based instrument, so it provides very high resolution information. The ASO team releases a snow depth product at a spatial resolution of 50 meters. This is their coarsest product. They also provide some images at as fine as 5-meter resolution. Those you have to pay for. This is obviously sort of far too coarse for evaluation of a model like WRF, right? So WRF is at best simulating things at 1 kilometer, 1,000 meters in our simulations. So what we did is we aggregated up to the spatial scale that we can use the WRF forcings at. It's actually chose a resolution of 250 meters at which he ran the land surface model to kind of compare with these ASO data. But in doing that aggregation, right, there's a couple of reasons for doing it. So comparing it to the hydrologic model, but also in doing so, right, we're aggregating out some of the things that you actually observe at much higher resolution. So things like avalanches that show up in nature and are an important process for redistributing snow in the landscape will show up in these 50-meter data, right? But if we aggregate up to 1 kilometer, we're sort of aggregating out that sort of form of redistribution, okay? So some snow scientists sort of will take issue with that, but as hydrologists, right, this is the best that we sort of can do to use these products to try and tell us how good our precipitation predictions are. So if we look at these comparisons, this is a comparison of the Airborne Snow Observatory, or ASO, snow depth data at a time of what we think of as close to the peak snow accumulation in the landscape. So this is March 31st, 2018. This is April 7, 2019. Universally, we think of as April 1 as about being the sort of peak snow accumulation time. And we're looking at the observation of snow depth from ASO here on the left, and the land surface model's interpretation of what the snow depth is with these different precipitation realizations associated with different microphysical processes. So these are the 3 WRF runs that Will did So he took the output of WRF and ran NOAA MP at a resolution of 250 meters. He also took PRISM data here and used it to force the NOAA MP model to produce a spatial distribution of snow depth that's associated with the PRISM data. It's a very commonly used data set for climatological precipitation in the continental United States, right? And what I'd like you to sort of see here, right? One of the sort of ramifications that we found here is that a challenge we have is that, okay, between March or between 2018 and 2019, right? This is a this is the variability that we see within a year, right? So within a dry year, between, for instance, the Jensen Ishmael microphysics model, the more sophisticated model, and the less sophisticated models, right? We see a lot of variability across these microphysics schemes in terms of the inferred snow depth or the modeled snow depth. So up to a meter within a year. And if we compare that to sort of the wet year, right, there's as much variability within this dry year as there is sort of in some schemes across a wet and dry year, right? So these microphysics schemes are sort of producing very different or associated with very different snowpacks within a year. And that's as much variability as we see across sort of wet and dry years. So the implications of these sort of findings are that, we need to sort of continue trying to investigate, right, the way that these microphysics schemes are predicting different precipitation phases and different precipitation amounts throughout the landscape. And we need to sort of continue communicating with our colleagues in the atmospheric sciences about the ramifications of the different choices that are being made and the different representations for microphysical processes, for sort of the land surface hydrological processes, right? So the results of this work is sort of a call that, we need to be in sort of continued dialogue with our colleagues in the atmospheric sciences about cloud microphysical process representations. So again, coming back to this idea of, well, how do we, what are other ways that we can sort of benchmark these model data sets? And a very common way, right, is to just say, well, I want to find, as many different products as I can. I'll kind of compute the differences in things like snow depth or precipitation, or in this particular case, we're going to compare precipitation across a number of different products. And I'm just going to sort of make some comments on how my precipitation product varies from these other products. So that's exactly sort of what Will did here. So this is a matrix of the simulated precipitation from WRF, the interpolated precipitation from the PRISM product, a product that Ben Livna at University of Colorado puts out, and another product that was developed by Andy Newman at the National Center for Atmospheric Research. So what we can do is just take all of these as just potentially different realizations of precipitation and then ask, well, how do they differ from one another? But one of the challenges in doing so is that the PRISM data set actually shows up in the Livna and Newman data sets, but it shows up differently, right? So PRISM is so broadly available and so broadly used that it's actually being used to sort of spatially distribute precipitation by both Ben's product and Andy's product. It's being used in different ways, right? And I'm not going to get into the nuances on how it's used differently. But the important thing here is that, these are not entirely independent comparisons, right? Because PRISM is actually showing up, the spatial distribution is showing up in all of these products that we're comparing to our WRF data. So maybe what we'd want to do instead, right, is impose some hydrologic constraints on our data, right? So ask, what is our degree of belief that the precipitation that WRF simulated is consistent with observed discharge and snow water storage? So what Will did is he extended an approach that Brian Henn developed in 2018, which is to basically say, well, we know pretty well what the distribution of discharge is we can come up with sort of different ways of representing the watershed processes. We can represent the structural uncertainty in our understanding of critical zone processes, and we can try and sort of invert for what the probability density function of precipitation is, right? So we can ask the discharge to tell us, we can ask the discharge and the watershed processes to tell us what the probability of precipitation is, and then we can ask where our precipitation product falls within that. An added innovation that Will added is to take this airborne snow observatory data and say that, well, we can also impose as a constraint that the snow water equivalent lapse rate, so the rate at which snow water equivalent changes with elevation, we can impose that from the airborne snow observatory data. So Will did a Bayesian model inference formulation. He developed a very simple bucket model. This is one of the models that's sort of within the Fuse model framework that Martin Clark at the University of Calgary developed. And this is a really simple hydrologic model that's easy to calibrate. And in doing so, this means that we can run this model, millions of times with millions of different realizations of precipitation, and use the discharge to sort of constrain which of those realizations of precipitation are more likely than not to have produced that observed discharge. At the same time, what Will can do is sort of, this simple model is sort of driven by a simple temperature index model for snow accumulation and snow melt. And what we can do is impose observed temperature and snow water equivalent lapse rates on that precipitation. So Will calibrated the model for a number of years based on discharge, and then used the snow water equivalent lapse rate from the airborne snow observatory data to subsequently sort of refine which of those model parameters were producing results that were closest to our to the observed discharge. And he was able to come up with a set of parameters for these 2 water years. And then, using only the SNOWTEL data at 2 different stations for precipitation and the airborne snow observatory data, produce a model that we could then use to sort of drive with a large distribution of precipitation, to then ask, so we could then drive that sort of simple bucket model with a large PDF of precipitation rates, and then use Bayesian inference to sort of assign posterior probabilities to those different precipitations, right? To sort of come up with an inferred precipitation based on our bucket model and our observed discharge data. So this is what we think of as maybe perhaps a more fair way to compare the WRF precipitation data with, for instance, the PRISM precipitation data, in order to ask how likely is it that those data products could have produced the discharge that that was actually observed, right? So in this case, we can compare what we think of as the WRF data in blue here, the PRISM data in orange, and the precipitation data that we think the discharge is telling us was likely to happen. One thing that we find when we sort of do this, so this is work that's now in press in GMD, is the length of the instrumentation record actually sort of starts to exert influence here. So if we look at this sort of last 10 years or so of data, what we start to see is that WRF and PRISM are somewhat different from one another for about 20 years, prior to about 2011, 2010, when all of a sudden they sort of start to agree more. So what's actually going on there? And what's going on there is actually really interesting, and that is that in the watershed, there is a new SNOWTEL station that is installed in about 2010. And for those of you that have ever used the PRISM data, PRISM is just a geostatistical interpolation of a bunch of surface observations, SNOTEL included, and it's a closed source model, so we don't exactly know how those data are being used. But whenever new observations come online, they then take those data and use them to sort of improve their predictions of precipitation. And so what we'll hypothesize is, and what we have some evidence to suggest, is that actually this change in agreement between the WRF and PRISM models wasn't necessarily sort of something going on with either WRF or our choices in the model, or some broader climatological trends, but is actually a product of the fact that this new SNOTEL station in the East River sort of came online in 2010, and you sort of start to see a significant shift in the precipitation statistics across that that time horizon, right, when that new observation was added. So this just sort of goes to show us that, again, we need to be careful when comparing these products, because the length of the instrumental record that is used in constructing these products varies, right? So observations drop out, new observations come in, and that shifts the predictions accordingly. And it should, right? That's the nature of these products, but it just means that we need to be really careful when we're comparing, things like simulations from WRF with things like PRISM precipitation products in these kinds of landscapes. So just to sort of wrap up and summarize, right, this is just a real quick summary. The high level takeaways, I think, are that the choices that we make when we use models like the weather research and forecasting model have really profound implications for the ways that the atmosphere interacts with topography and ultimately produces predictions of precipitation. Those differences in predictions have important implications for the way that we predict that the snowpack develops and ablates. That then sort of has really important implications for the timing, rate, and spatial extent of water delivery to the critical zone. Something I didn't talk about today is that there's some field campaigns. So coordinated field campaigns are really essential to sort of providing the data for atmospheric scientists and hydrologists like myself to be able to converse and be able to look at the same data in slightly different but complementary ways. But evaluating these precipitation data sets is both important, but it's also difficult. And it's often hard, for very good reasons, to find data sets that are completely independent of one another. But we can start to think of, the way that we're evaluating these data sets, right? We're coming to this from a hydrologic perspective, which is not so much, certainly getting the distribution of precipitation in space and time correct is really important. But also what's important is, how likely is it that this precipitation produced, or my predicted precipitation, produced the hydrologic response that we actually observed, whether that's, in this case, discharge, but in other cases, for instance, the soil moisture response or the evapotranspiration response. And so, this is sort of a really interesting and sort of, I think, fruitful future dimension as well, right? Another way for us to sort of engage in conversations across the atmospheric and hydrologic sciences, which is to ask, how can we evaluate atmospheric data sets through the lens of hydrologic and critical zone scientists? So with that, I want to thank you all. This research was supported by a Department of Energy Office of Science grant, and I'd be happy to take any questions that you all have.
Thank you so much, Alejandro, for that very interesting talk. So yes, if anyone wants to follow with a couple of questions for Alejandro, please speak up.
Okay, I'll jump in quickly, Alejandro. A nice talk. I was just curious, once SNOTEL data point made so much difference? I mean, is it at a point location, or is it an aerial average, or?
Yeah, so that's a great question, Praveen. So this figure is sort of showing the individual sites, the individual SNOTEL stations themselves, right? And the prism kind of the prism aerial averaged for the East River. And so for the time to the left of this dotted line here, this is the East River average precipitation. The average precipitation in green, right? And these individual stations in I guess orange and blue, right? And then this new station is shown in red. And so, you know, what happens is that you know, so we could ask ourselves, okay, where does this new station fall relative to these other SNOTEL stations? And
Right.
if Prism is in fact sort of doing some kind of, you know, geostatistical averaging of these stations, then what we would expect is for this new station, you know, for the average precipitation estimate to be pulled in the direction of this sort of new station. And it turns out that this new station is in a location, I think it's actually in the neighboring Taylor River watershed, where it's kind of below this station 737, which I think is the Schofield station. 380, I think, is Butte, right? So it's lower than the higher, you know, the station in the region that reports higher precipitation on average. And so we would expect the average, or we would expect, if this station's introduction is important in time, we would expect, because this precipitation is sort of more closer to Butte, the average precipitation for the East River to sort of be pulled down, right, in the direction of this new 1141 station. And that's sort of you know, exactly what sort of happens with this average precipitation, and it's sort of statistically significant. So, you know, there's still some questions that we have about this, but it's at least consistent with our mental model of how this introduction of a new station would affect the statistics.
So I would imagine that the new station was introduced essentially to cover some gap in the heterogeneity. And so when that was done, then it catches up a little bit better, or reflects better what is going on in that, because that's a pretty complex topography and crested butte.
Exactly. And I think that's exactly right. And I think that that's actually what's sort of happening. And this, right, so I want to say, right, this is, you know, this is a messy plot, but we want to sort of make the case that in fact our precipitation is perhaps a little bit better than Prism in this historical period, because, right, Prism is dependent on, you know, prior to 2010, a station that is just located in a place that's catching more precipitation. And in fact, when you introduce that new station in 2010, that drags the Prism estimate towards what we think of as being perhaps more correct, but it results in sort of a decrease. The Prism predicted precipitation, right, is a decrease in precipitation, or is decreased after 2010, but it's actually because that new station is pulling it closer to reality, because you're exactly right. They added that station because it was in a location where there wasn't good spatial coverage, and the precipitation is sort of spotty from year to year. It's a higher elevation site, but it usually gets lower precipitation.
Thank you.
Yep.
Anyone else? I have a question for Alejandro.
I do too.
Yeah, Erin, go ahead.
So you can go first. I don't
No,
know.
no, go ahead, Erin.
Okay, so I run a precipitation network that's been going on for 30 years, and the grid of it's 19 stations, and the grid is about 6 miles between gauges. It's paired with equal number of groundwater wells, so we have groundwater reaction to it. But my question is, this, oh, now I just, explaining all that, I thought, how much do I need to explain before my question? And now it's just gone. Why don't you go first and I'll think of my question. I had so many questions and then I picked one and yeah, go ahead. Anton?
No, I'm moderating. I don't have any question right now.
I have a question. So in this plot A here, the kind of early stages, the green, the inferred precipitation, has a lot larger of an error bar, and it kind of seems like those go down through time. Is that because of a climatic change, or is that a improvement in the model over time, or?
Yeah, that's a great question. And thanks for that, Brian. I think that actually, you know, there's a couple reasons for that, right? One is, yeah, I mean, one has to do with sort of some of the assumptions of the prior distributions that we make on precipitation, right? And you know, and part of that is sort of based on the fact that right, this is like early 90s, right? And so this is at this point sort of 30-ish years ago. So we think that there have been some large climatic trends there in the Colorado Rockies and elsewhere in the Western United States over that time. And I think that, you know, that is, you know, that's one reason, right, we think of is that, you know, the range of sort of precipitation used to be, well, there used to be sort of much larger sort of precipitation years, you know, or that large precipitation years were sort of at least more frequent in you know, even sort of 30 years ago. And so part of this, I think, is due to sort of climatic shifts in terms of the precipitation. I think the algorithm is maybe having a hard time sort of reconciling those because they're sort of less frequent when it's doing it sort of like the Bayesian inference, right? So I think that it's, you know, some of these years it's more just that it's having a hard time kind of converging on what that sort of distribution of precipitation is. Another thing I think that Ben Livna has pointed out in some of his work is that there's actually sort of, you know, the Colorado Rockies are somewhat complex in that, you know, sometimes there are these years in which you'll get sort of a large sort of precipitation year, a large snow year, but then you'll have sort of, you know, a relatively, you know, hot and dry spring, you know, which, you know, results in sort of a lot of depletion of soil moisture that would, you know, keep that hydrologic connectivity sort of going. So, you know, Colorado and mountain regions in general can be some of these places where there's sometimes sort of a weird decoupling between the precipitation and stream flow, right? In which, you know, you can have high precipitation years, but still wind up with stream flow drought. And there's a whole bunch of additional processes there that are sort of worth kind of digging into that we're not here. So I think that you're seeing a little bit of both of those.
Thank you.
Okay, I'm ready. So with that said, with this network, so the network edge is parallel to a river valley, and there's a significant bluff from the river valley up. It's along the Illinois River. Significant, I don't know, significant in that there is something there for Illinois. It's orthogonal to the prevailing wind direction. And so what I'm finding in this long-term data set is that it seems like there's a river effect or a topographic effect where the systems will come across and then they'll have the highest precipitation near the river and then lower going out. Does your model, can your model then take these topographically challenged areas with this slight topography variations with you know, rivers that would provide more moisture to storm systems and then drop them closer on top of the bluff and then less so as the storms kind of dissipate? to the southeast. Is
Yeah,
that
that's a
seen, or
really
is that already documented in literature? It's just not my thing to like dive into all that stuff, but I'm just curious because it's like a thing I see all the time.
Yeah, no, that's a really interesting question, right? I think that in terms of like the weather research and forecasting model, right? Illinois, I might be totally wrong here, right? But I think that there's a really strong dominance of sort of you know, convective sort of summertime storms, you know, that often are sort of more produced by sort of atmospheric instabilities, right? And
We
but
call
are
them
sort of
pop and drop.
What's that?
In the field tech sector, we call them pop and drop.
Yeah, pop and drop. Yeah.
Yeah.
Right. And so you know, that's the whole area of these models that is right. So the convective parameterizations, right? One of the reasons we go down in scale is just that those convective parameterizations are very difficult to sort of resolve, right? And so I'm not sure that in Illinois, you know, the topography would be sort of enough to produce some atmospheric, you know, some forced convective motions, you know. But what is interesting, right, is that it is the small topography that you're seeing, coupled with sort of redistribution of water in the subsurface. I mean, Praveen might have the answer to this. You know, is that sufficient to actually result in some, you know, enough enhanced evapotranspiration in the vicinity of the river corridor to trigger some of these, you know, convective movements that would result in more precipitation locally?
Yeah, so I don't see that particularly. I don't see the pop happening on the east side of the river. I'm seeing this more in systems that are already developed on the west side of the river or the northwest side, and then they come across and then they gather even more moisture, I'm thinking, and then in the initial front of the storm, it seems like it drops more precipitation on the east side of the river valley as it's coming from the northeast, and then you know, and then less so later on, even if the system kind of keeps going through. I mean, it's the whole county, so it's like even like a 35-40 mile stretch. So anyway, I'm just curious.
Yeah, no, it could be that there are some like small sort of topographic interactions that are important. I think it's right, like you might with a model with models
and
like
because
this,
the river is right there. I mean,
yeah, like
yeah.
and you might have to get down to even finer spatial resolutions to sort of tease out some of those nuances, but that's a really interesting sort of a fact.
That's all I have.
Well, thank you for interesting questions. I think it's time for us to wrap up. And just before we end, so thank you again, Alejandro, for that very wonderful presentation. Before we go, I just dropped in the chat a link for a survey regarding CINet outreach. Please take a couple of minutes to fill it. We've been asked to communicate on that so that we can get better outreach, I think. I can display a QR code if it's easier for you. Other than that, just you can click the link in the chat.
Thank you, Alejandro.
Yep. Thank you all. Good to see you all.
Thanks so
Have a
much.
great day.
Thank you.
Thanks, Antoine. Yeah. Oh, okay. Never mind. Thanks.
Yeah, well, there's no one anymore. Well,
Yeah.
I tried to get the link out. Maybe we can just like flow it. We can just like send the link to the attendance list.
Afterwards. Yeah, that's a good
Yeah.
idea.
I mean, I
Okay.
guess it's gonna do the same job anyway. Like if people click and fill in the thing, it's good.
Yeah, that
Right.
makes sense.
Thanks,
All right,
everybody. See you later. See you tonight.
see you.